let's continue our journey through Stable Diffusion AI, or more precisely, generative AI. Today we will discuss together some brief overview how Stable Diffusion works. When I started learning about Stable Diffusion, these pages helped me a lot. StableDiffusionArt.com. So it's only fair to return back by making these pages known to others. So let's use these pages and let's go together through article how does Stable Diffusion work. So before we start, what is even Stable Diffusion model? So it's deep learning model. Deep learning means that it's trying to mimic learning principles from human brain. It's generative model, which means it generates something a little different as output than what you trained the model against. It's text to image model, which means you input text, what you want to see, and as output you get image. And the reason why it's called diffusion, it's because when you describe the process mathematically, it looks like physical diffusion. You can imagine dropping an ink into the water, and then after some time the ink will diffuse into water, and then you won't be able to tell that there was any ink dropped into the water. So let's kick on and see what the Stable Diffusion can do. So as I mentioned, and as we can see here, it's text to image model, so you enter some text, run the text through the model, and you get some images. When we train the model, we use something which is called forward diffusion. So in this case, we can see there are two groups. There are cats and dogs. And when we simply do a forward diffusion, we end with something like a random noise images. So when we run it through the model, we end with these random noise images. So here we can see it one more time. When we are training model using the image, it just adds a random noise into the model. And as it flows through the model and it's changing the weight, it simply adds random noise, and we end with random noise picture, so we can't simply tell if it was cat to begin with. Now, if we want to reverse the diffusion, which means from the trained data we want to get back either cats or dogs, but definitely the outcome of reverse diffusion would be something a little different than the pictures that we've used for training. So how can we do it? In case of Stable Diffusion model, it was solved in a way that we train a so-called noise predictor. So it looks like this. We add a random noise, then we train noise predictor to be able to tell that we add this amount of noise, then we again add another layer of noise to the picture, and we again train the noise predictor to be able to tell us, okay, now there is noise added 2 times, and so on. And we end with a model that can predict how much noise we add to the picture, to the original picture. So now you may probably start to see that if our training ends as a random noise, and we also have something which can predict the amount of noise added to the picture, and we combine these two things together, and then we subtract from the random noise image the predicted noise, Then after several steps, we will end with an image. Of course, at this point, this is going to be random. So if we just use our noise predictor and we trained the model on the pictures of cats or pictures of dogs, we will in the end randomly end either with a cat or dog. But this is not what we want to do. We would love to be able to steer the model, or more precisely the noise predictor, from this random noise to subtract the noise and provide us with a picture that we want to see, be it cat, dog, or something else. So how is this solved in case of Stable Diffusion? We will figure that out in a while, but before we get to that, amazing thing about Stable Diffusion model is that they figured out a smart magic how to compress and work on much smaller space. So we need much less power to compute it. And that's the reason why Stable Diffusion can run on our home graphic card with just 8 gigs of memory. So normally if we take picture which would be 512 multiplied by 512, and we take into account there is actually RBG and there can be also other layers, then simply this image space is huge. So if we would be working with a random noise and removing the random noise in such space, we would need many graphic cards. But in case of Stable Diffusion, what they did, they created some transformator or compressor that is able to move from image space into so-called latent space. And the latent space is 48 times smaller. So, of course, on a smaller space, we can simply run much more calculations and do these calculations faster. So that's the reason why we can run this Stable Diffusion model locally. The component which is responsible for moving from image space into latent space and then from latent space into image space, it's called a variational autoencoder, or VAE in a short. So this is smart magic behind Stable Diffusion that allows us to run it locally because it significantly decreases the computational power. One thing which is good to keep in mind, the models of Stable Diffusion are usually optimized for some precise resolution. For example, in case of model version 1.5, it's usually 512 multiplied by 512. In case of the latest SDXL model, I believe it's twice as much, which is 1024 by 1024. If you try to use different resolution with model which was not trained for it, you can get some artifacts like double heads and so on. So this is just good idea to keep in mind, to use the resolution that model was trained against, and then you can upscale after you generate picture that you like. So now let's move into the conditioning, because currently we are able to train the model. We will end with some random noise, and then from this random noise we have our noise predictor, so it's able to subtract the noise and reconstruct the image for us. And because the Stable Diffusion is generative model, it will be something a little different than the data we trained this model on. This is very nice, but still we are not able to control what will be the outcome. And this is done through so-called conditioning. So if we see, here is our noise predictor, and here is the conditioning pipeline. So we enter some text, but unfortunately computers are not able to understand text. So we use a method which is called tokenization. I believe Stable Diffusion is using the clip tokenizer from OpenAI. And the tokenizer is responsible for creating for us the numbers which corresponds to words, or more precisely, they correspond to the data it was trained against, because sometimes if the tokenizer sees unknown word, it can split it into two tokens. So single word can be two tokens. Then we have something which is called embeddings. And embeddings is just a vector which is trying to represent how these words may be interconnected together. For example, guy, gentleman, these would be very likely close to one another. On the other hand, for example, car and man, these two things would be inside totally different groups. So embeddings are trying to simply merge the similar concepts together, and then they are fed into text transformer, and text transformer is then feeding into several layers of our trained noise predictor, which is subtracting the noise from random noise picture. And by that, in the end, it will generate for us the picture, or steer the diffusion in the picture we want to see. And because it's fed into several layers, we achieve something which is called cross-layer awareness. And it's similarly like in case of human brain. If we mention that we want to see a man with blue eyes, or man in a t-shirt with blue eyes, then by noise predictor being able to use cross attention in between layers, it understands that the eyes should be blue and not the t-shirt should be blue. So it works similarly like in human brain. And that's pretty much it. That's pretty much how Stable Diffusion works. Now, of course, if you want to have a deep understanding or deep knowledge, I definitely encourage you to read through this article, because, I mean, it's amazing